Thank you so much, Professor and audience, for giving me the opportunities for today's presentations. And good morning. Today, I would like to talk about uh, my master's degree presentations. So my research title is the dimethyl ether is produced directly from carbon dioxide using catalyst based on the copper gallium aluminum oxide catalyst. And I am Uday Soms. I am the student of the Applied Chemistry and Biochemical Engineering, Department of Engineering, Graduate School of Integrated Science and Technology, Shizuoka University, Hamamatsu campus in Japan. It's a so my next slide. So today I'd like to talk about this presentation outline. So firstly, I talk about the background of the research in my research and also my laboratory backgrounds. So after that, I would like to talk about my objectives, my purpose of my research. After the what kinds of materials and method I used in my laboratory, and also I have. After that, the conclusions, and I take some reference about these things. So firstly, we need to know about the biomass and gasifications. So after that, this biomass and gasification, I would like to produce the syngas. Is carbon monoxide, carbon dioxide, hydrogen, and this syngas we get the main products. After that, we get the byproducts. Looks like the tar and char. Dislikes. Uh, So this after that we get the energy, gas turbine, liquid fuels, DME, diesel, octane, kerosenes. So in my laboratory purpose, we produce the DME is the dimethyl ether. So we need to know the what is dimethyl ether. So dimethyl ether is the simplest in ether and is neither be toxic or carcinogenic molecules. And the DME is the uh, it also the liquid at the room temperature relatively low. This pressure is uh, mega. Mm, Clean fuel alternative to liquefied petroleum gas is looks like you can alternatively in the LPG diesel engine power generation in gas turbines. Propellant of cosmetic products. It's also used and used in the chemical intermediates for light olefins and the synthetic gasoline productions. So DME burns without no particulate matters. It's also the sulfur-free properties and low emission of NOx and carbon monoxide. Also the SOx also. So DME is high seated numbers and easy to carry and storage of hydrogen and energy. After that, the next slides, that DME is the simplest in ether and it is also colorless and transparent gas. I also show these pictures also how can we use the DME and the application also. And it is also use the multi-purposes and multi-sources clean fuel for the variety of applications. Is I already told the gas turbines, fuel gas, and feedstock of organic substance. So these slides, I try to look down the DME productions. The firstly, we need to know the DME production is produced by two types. The DME synthesis is produced is two different methods. Looks like the one method is the direct synthesis and another is the indirect synthesis. So the direct synthesis of DME is an ideal and which requires only one reactor. Is cheaper than the indirect synthesis. So after that, the indirect synthesis of DME, the methanol synthesis reaction and methanol dehydration reaction are performed perform in the CPATS reactors. So firstly, the carbon dioxide hydrogen over copper based catalyst by the Sol-Gel method. In my laboratory also done the Sol-Gel method is more effective than other preparation methods. There is many different types of methods. Is the precipitation method, is stritration method. So I already done the Sol-Gel method. Firstly, we need to we need to react it with the CO hydrogen to DME. This is the direct process. So 3 mole of carbon monoxide and 3 mole of hydrogen, we get the DME and the carbon monoxide. After that, if we separate these reactions, so carbon monoxide, hydrogen to methanol, firstly we get the methanol. Is this reaction carbon monoxide and hydrogen and produce the methanol. After that, this methanol dehydrations. Dehydration means is the separate the water. So 2 mole of methanol, we get the DME is the main product and we get the byproduct in the water. So after that, this is my main reactor, this is my main product, but beside in the reactors, beside of the reactors is the byproduct is occurs in the reverse water gas shift reactions. So this reaction is occurred in the carbon dioxide and hydrogen and get the carbon monoxide and water. So in my research study and the research purpose, I would like to know and I would like to investigate the effect of the reaction temperature on intermediates by FTIR spectroscopy. After that, we get the intermediate products. After that, I try to formation of the reaction mechanism according to the reaction pathways over the copper-based catalyst. So I already done the copper zinc aluminum oxide catalyst. So my laboratory is the copper-based catalyst. So after that, I get the good results. After that, I take the copper gallium aluminum oxide catalyst. So in the slides, I try to show the experimental apparatus. How can we take and how can we get the catalyst? So firstly, the copper gallium aluminum oxide catalyst was prepared by the consecutive Solzen method. So firstly, in 1000 ml hot water take and added it in the AIP. AIP is the isopropanyl acetic acid. After that, the ethylene glycol is easy and diluted nitric acid. The pH of the solution is maintained around 1 to 2. After that, the aqueous solutions of copper and gallium nitrate is added at this part and get the boehmite sol. So the clear sol was evaporated by reducing pressures and remove the water. So after that, the octane gel was dried at 170 degree temperatures and after the calcinite at the 500 degree temperatures. The powder grade is less than around 150 micrometer and 20 gram copper gallium aluminum oxide catalyst was obtained. So the obtained catalyst is measured by the FTIR spectroscopy. So the reduction and reaction were performed in the FTIR spectroscopy. So after that, in this catalyst, I put in the FTIR measurement conditions. So firstly, we reduced in this catalyst. So the reduced reaction is the hydrogen, carbon dioxide, argon. Argon is working in the carrier gas. And this is the FTIR spectroscopy. There is some have some equipment, looks like the MCT detectors. After that, the evacuations and the heat chambers. So, and after that, we try to investigate the soap film flow meters. My flow is how much I flow in my gas, we can see from the soap film flow meter. So firstly, the reduced conditions. So reduced condition is my laboratory is hydrogen feed rate is 10 milliliter per minute. The temperatures around 300 to 750 degree temperatures. And the reduction time is the 5 hours and the catalyst weight is 14 to 20. So after that, the reactor temperatures. So after finishing the 5 hours reductions, we and the gas is the hydrogen carbon dioxide argons is uh, and pressures in the 0.9 megapascals. So in the slides, I try to describe about the carbon dioxide hydrogenations over the copper-based catalyst. Firstly, the catalyst was reduced at different temperatures from 300 to 750 degrees centigrade temperatures in the flow of the hydrogen 10 milliliter per minute. And the carrier gas is the 1 hour argon. So the temperature is increasing from 25 degree temperatures. After that, I done the 300 degrees centigrade temperatures for 5 hours. After the 450 degrees centigrade temperature, 600 degree temperatures, and 750 degree temperatures. This is my reduced temperature is different temperatures. I already done. So after finishing, we cool down in my experiment in the FTIR spectroscopy. So after that, the FTIR, the 300 degrees centigrade temperatures, after that, we reacted. The reaction flow is different. Is the hydrogen 15 milliliter per minute, carbon dioxide 5 milliliter per minute, and argons 2.0 milliliter per minute. So I show this is the reaction pathway and the reduction pathway. So room temperatures is 25 degrees centigrade temperatures. The hydrogen reduction 5 hours. After that, we gradually done. Degrees centigrade temperatures. In my laboratory, members already done the 260 degree temperature is the good production for the DME. So that's why I try to maintain this temperature is from 220 to 260, and after that I get the intermediate products and try to make the mechanisms. So in the slides, I try to show about the result and the discussions. These slides I try to show the intermediate products I get over the copper-based catalyst at 220 degrees centigrade temperature, reactor temperature. So in this deep spectrum over copper, gallium, and aluminum oxide catalyst, the calcinide is the 800 degree temperatures, reduced at the 600 degree temperatures, and the reaction temperature is 220 degrees centigrade temperature. So if you see the wave number around 939, 979, 1129 represents the DME stretching this. So there have some noise peaks. So the absorbed peak of formate carbonate carbon monoxide is shown. The peak number is the 1337, 1385, 2032, 2075. So the wave number from 2700 to 3500 represents the smaller intensity peak of the formaldehyde hydroxide. So the formaldehyde is show the peaks of the 2750 and 3429. So in the slides, I try to show the intermediate products at the 600, 500 degrees centigrade calcinate temperatures, reduced at 600 degree temperatures and 240 degrees centigrade temperature in the reaction temperatures. So if we see the wave number around 939, 979, 1129 is represents the DME stretching. The carbonate carbon monoxide were 1337, 1385, 2032, 2075. So the wave number from the 2700 to 3500 it represents the smaller intensity peak of the formaldehyde and hydroxyl. So the formaldehyde and hydroxyl peaks are show is the same before the similars 220 degrees centigrade temperature is 275 2750 degrees centigrade temperature. The wave number 1429 and the formic is 1755. So in these slides, I try to show the intermediate products over the 650 degree centigrade calcinate temperature reduced at the 600 degree temperatures, and the reaction temperature is 260 degree temperatures. So if we see the intensity of the DME, methoxy, methanol stretching are similar to the other reactor temperatures. So the intermediate peaks of formate water hydroxyl group are sharp peak at the 260 degree temperatures, reactor temperature. So we can say is the different reaction temperatures is 220 degree centigrade temperatures, 240. So we get the good peak of the 260 degree temperatures. So in these slides, I try to show the deep spectrums of the methoxy stretching over copper gallium aluminum oxide catalyst by using the sol gel method. And this stretching, I show the methoxy is calcinite 650 degree centigrade temperature, reduced 600 degree, and the reacted temperature is 240 degree temperature. So FTIR is a fast and non-destructive strategy for the quantitative and qualitative analysis of different components. So the peak of the methoxy species shows the wave number is 1031, 1082, and 1100, this wave number. So the methoxy peak was increasing for the absorption of carbon dioxide flow rate onto the catalyst surface. So after that, in these slides, I show the methanol stretching. The calcinate temperature is 650 degree, reduced at the 600 degree temperatures, and reaction temperatures 240 degree temperature. So this figure, the deep spectrum of the methanol CO stretching shows a strong absorption band of carbon hydrogen stretching vibrations. So the presence of methanol stretching peak is assigned at 1750, 750 wave numbers. Owing to the inductive effect of the carbon and hydrogen atoms, the frequency of CH stretching corresponds to HCO, create a weaker. So the hydroxyl group is represents in a broadband area of the spectrum. So, so after that, in the slides, and I am trying to investigate the intermediate products depending on the interval time at 240 degrees centigrade reactor temperatures and constant pressures is 0.9 megapascal. So the often carbon dioxide and hydrogen mixtures at 240 degrees centigrade temperatures, pressure is 0.9, and for the interval time is the 9 hour. So the intensity of the intermediate is gradually increasing from up to 2 hours. So the absorbed intensity of DME, Formate, formic acid, species fastly increasing with increasing the interval times, so that the catalytic activity was shown with increasing the interval times. I try to show these things. So after that, these slides, I try to show the XRD characterizations in my catalyst. So there is different calcinite temperatures is 300, 500, 350 degrees centigrade temperatures, 5-hour calcinations. There is no reduction occurs. So after that, the 500 degrees centigrade temperature calcination for 5 hours, there is no reduction. Temperature 650 degrees centigrade temperature for 5-hour calcination, no reduction. And also the 800 degrees centigrade temperatures, 5-hour calcination, no reductions. So if we see the peaks, increase the calcinite temperature from 350 to 800 degrees centigrade temperatures. If we see the crystalline peak of the copper aluminum oxide, the copper aluminum oxide peak is 31.22 and 36.82 degree was increasing at the 800 degree temperatures, calcinate temperatures. Because the photolytic activity of copper aluminum oxide catalyst surface area is larger. So the copper oxide showed higher peak at lower temperatures of the higher crystalline size. So the copper shows higher peak for higher temperature. For copper based catalyst. So after that, these slides, I try to show is different calcinite temperatures, also the different reduction temperatures. Different means I try to show, today I would like to show the constant calcinite temperatures and different reduction temperature. What should be occurs? So in this figure, the XRD characterizations at 800 degrees centigrade temperature calcinations and different reduction temperatures. So if you see the increase, the reduced temperatures from 300 to 750 degrees centigrade temperatures, the crystalline peak of copper aluminum oxide catalyst was decreased because the photolytic activity of copper aluminum oxide surface was decreased. Before we show that the different calcinite temperature, we get the good copper aluminum oxide peak, crystalline peaks, but there is not occurs in the reduction. So the reduced lower temperature peaks of copper aluminum oxide shows higher because the surface area is higher. The copper crystalline peak was increasing because of the reduction of copper oxide particles. So small copper oxide crystal means high dispersion of copper. After reduce the copper oxide, no peak shows, but before reduce, they get higher peaks. Diffraction peak of the intensity may vary slightly at different growth temperatures. So increasing the reduced temperatures, the peak intensity is lower because of the lower crystalline size. So lower temperature peak is higher for the higher crystalline size of the gallium or gallium oxides. So in these slides, I try to show some charts, the catalyst calcination and reduction temperature, and how can I get the BET surface, the pore volume, pore diameter, surface coppers, copper dispersion, and copper particle size. So this chart is important for characterizations for the surface area, copper particle size, pore diameters, and copper dispersions. I try to write down in my left side in this table. So calcination and different calcination and reduction temperatures. I occurs and I get the surface area. So after that, in these slides, I try to show the carbon dioxide activations. Proceed to copper catalyst in the two mechanisms. So there is occurs in two types of mechanism. Firstly, the Formate mechanisms. After that, the reverse water gas shift reaction mechanisms. So Formate mechanism in which carbon dioxide hydrogenations proceed via the Formate intermediates. Formate intermediates. So where carbon dioxide is converted to carbon monoxide and then the methanol oxide via hydrogenated intermediate. So the first intermediate is the Formate species. Attach involve the lattice oxygen atom on copper oxide catalyst. The CHO formyl hydrogenated to formate the methoxy. The formation of the methoxy species kinetically relevant aspect for the methanol synthesis on copper base catalyst. So the hydrogenation of the carbon dioxide and hydrogen occurs in the copper gallium oxide. So the support of the aluminum oxide catalyst is after that the methanol is synthesis. After the methanol is formation, the methoxy species react with the surface proton to produce the methanol. On the copper gallium oxide side, the methanol hydrogenations occur on the aluminum oxide catalyst acid sides and produce the DME. So in this figure, I try to show the proposal of the carbon dioxide hydrogenations mechanism over copper gallium aluminum oxide catalyst. So firstly, the activation sites of the carbon dioxide leading to the formation of the methanol, they are undergoing the methanol oxide catalyst. So the absorption of carbon dioxide and hydrogen on the copper base catalyst occurs in the several way. Firstly, the carbon dioxide hydrogenations goes through the Formate intermediates. After that, the hydrogen of Formate leads to the formation of deoxyethylene. So deoxyethylene would be further hydrogenated to produce the CH3O2 by splitting of its OH group from CH3O2 transformed to the formaldehyde. So the hydrogenations of the formaldehyde get yield methoxy. In the final hydrogenation of the methoxy formates to the methanol. So after that, in the next reaction is the methanol dehydration. So the methanol dehydration is right side of the methanol gives alcoholic oxygens in the another methanol. So there is two methanols. After that, the nucleophilic substitution reactions occurs. The removal of the water and protonated the DME format. So the water molecules deprotonated the intermediate transferring back to the proton to the aluminum oxide catalyst supports which regenerates the acidic sites and finally DME is formed. So I try to show the summary in my research. So the active sites and the reaction pathway for carbon dioxide hydrogenations over copper gallium aluminum oxide catalyst. The copper and were investigate. I try to investigate by the operando drips techniques. After that, the carbon dioxide activation of the on the copper surface obtained the suitable format methoxy, methanol, and DME intermediates at lower temperatures and the higher pressures. So in this study, the copper-based catalyst showed the high stability and activity performance at 240 degrees centigrade temperature and 0.9 megapascal pressure. So I try to understand and show some reference. I recommend. So if you need any information, you contact me and also I write down this reference. You also get the many informations from my research or something. Thank you for your kind attention. Thank you.